Hello, everyone. We're going to get started now. Our speaker today is Steve Bernsen. Steve is a PhD candidate in the Department of Earth and Climate Sciences at the University of Maine. Steve did his undergrad in geology at Portland State. He also did a minor in physics for the physics people in the audience. After that, he did a master's in geophysics at the New Mexico Institute of Mining Technology. In there, he also worked in seismic applications at the Washington Department of Natural Resources and at the University of Alaska in Fairbanks, where he did work that was relevant to the Non-Proliferation Treaty. Steve is also maybe known to you as the owner-operator and baker at the Alfred Bread Co. You can sample his wares over there. So take it away, Steve.
Yeah, thanks. Thanks for coming. Seismic electromagnetic wave. Sounds pretty simple. There's a lot of stuff to unpack. So if you have any questions, if I'm losing you, just raise your hand. Don't get to a lot to learn. There we go. I'm colorblind, so sometimes I won't see this. So if I'm all over the place, I apologize. Chris Gerby, my advisor. Seth Campbell, also an advisor up at University of Maine. Knut Christensen, Washington, and Senthil Bell at University of. So they've done a lot of stuff, very broad. Oh, yeah. I could use that. I mean, I could tell you everything with one slide. If anybody knows Wally Broker, I went to talk with him and he did a whole hour on just a title slide. So as I said, talking about ice, a few definitions. Ice, I'm going to put it in the context of glaciers. That's primarily my focus, but ice comes in many forms across the universe. Ice 1H is what most of us are familiar with. So that's your standard hexagonal ice. Ice 1C is cubic ice, typically found in really cold temperatures, negative 100 C. You'll find that in the upper atmosphere. It's a crystalline inorganic substance, H2O. That's its primary form. And the nice thing about that, the H2O molecules get closer together. They form hydrogen bonds, which are fairly weak bonds compared to covalent bonds. So that allows some very interesting properties with ice. So to actually expel things that aren't part of the H2O lattice. And so sea ice will oftentimes separate into briny layers or salt layers, and then the ice will kind of self-purify itself. You'll see different kinds of ice, ice 2, ice 3, different crystal classes within these. They have different properties. None of those have been discovered on Earth. Ice 9 is also a thing. It's not a weapon of mass destruction, though. It's been produced in a lab. I won't get into those. Ice 1H is my primary concern. It's transversely isotropic. I'll talk a little more about that. That means that in different directions, it will exhibit different thermal, optical, and mechanical properties. Wave propagation sounds pretty simple. It's basically energy that's being transferred from one location to another without the permanent transfer of matter. And then bread. Bread is organic, porous, cellular solid. I have to read this because it is very. My background's in inorganic molecules, not so much organic, but it's formed by a lot of these gluten molecules. And these kind of form this sort of viscoelastic network. Viscoelastic has very similar so the gluten will have kind of similar properties as, say, something like ice. I kind of like it. It's a nice sandbox for me. So you can kind of look at the bread, and it has a lot of different like plastic behavior similar to ice. It's right now, it's not a big topic of the discussion. It's just for your enjoyment. But you can kind of look at it. It's nice talking about wave propagation and deformation. You can kind of, with the air bubbles, kind of give you a good reference to see how things deform based on how you apply stresses, different kind of strain. All right, so ice, why seems pretty, I don't know, fundamental, but why is it important? This is a snowfall, annual snowfall, contiguous US. It's a little bit older, but these maps are very, very useful. So there's a lot of information you can get from one of these. Big thing there is Great Lakes, one of the snowiest places in the US. And then you see the Rockies, a lot of snowfall comes through there. So a lot of important information from different fields of study can use this. Civil, if you're living in the Northwest, you need to know how much salt you need to order every year, how much gravel you need to have on hand. Texas, going to be a whole different story. The distribution of snowfall is changing with different types of weather patterns, which are, a result of changes in the climate. But ice, there are no glaciers in the Northeast, not until you get further north. I grew up in this little part of California here, southeast part of California. No snow, no ice. It's a very exotic thing for me. So this is within the Colorado River watershed. Colorado River comes up through here and collects water from all of these tributaries that come out of the mountains. So there's still a few glaciers in Colorado. It's southern. It's out near what is that, Durango, Four Corners area, San Juan Mountains, Yellowstone. Still some glaciers still alive there, and then you get up into glacier. From here, I moved up to the northwest. Columbia River Valley comes out of Canada. It's fed by quite a bit of snow and rain and glaciers. And then the Cascades here, these big stratovolcanoes that poke up, collect a lot of snow. Big glaciers on Mount Rainier, Mount Baker up here, record snowfall in the lower 48. And then we're looking at Mount St. Helens down here. So with this, glaciers, they kind of present a resource for us. The summer months, they melt, they provide us with water when the rain stops. They're big reservoirs for water. The big reservoirs for water that we need to maintain our municipalities and agriculture. So I don't want to get too much into doomsday stuff, but they are very significant. They cover 10% of the Earth's land area. That has large effects on the surface, the energy flux at the surface. So changes in that 10% are going to drastically affect how much energy is incident on the Earth. 2% little over 2% of the Earth's water is stored in glaciers, and that's going to be fresh water. That's quite a bit if you consider how much water is on the Earth. The volume of ice, it's massive in Antarctica. Antarctica is 2/3 the size of the US. It's completely covered in ice. So it's massive. Antarctica has the potential to release a lot of fresh water into the ocean. It's widely studied because it has a lot of impacts on sea level rise. Greenland as well, quite a bit of ice there. And then alpine mountain glaciers, a very small percentage, but they're very significant because we're in such close proximity to a lot of the alpine glaciers. This is a newer study. It's really interesting. Starts around, say, 95 to about just 2015, so a little more than 20 years of data. And this is kind of it's a big change in ice mass, and we see a lot of it is coming off of these alpine glaciers. So my background is more into alpine glaciers. They're a little more relevant to me because they do feed agriculture. Grew up in an agriculture area, so I'd like to see these things more work being done on these, more focus. Little joke. Was it the why does climate want privacy? It's changing. So getting into kind of glaciers and sort of this whole ice cycle. And if you're, so ice, snow falls, it's sediment. As it falls onto the surface, it gets covered up by more snow that collapses it. You have pores collapsing, you have sintering, you continue to pile more snow on, you have more overburden. Eventually the snow densifies into firn, which is about 750, 850 kilograms per cubic meter, a little more than that. And then you have glacial ice. You start to kind of get rid of a lot of the pore space. If you have melt of the ice, you're looking at magma, lava by definition. It'll refreeze via just changes in temperature, regelation, or frazzle. Frazzle is when you have these super cooled water, and once the pressure is removed, it'll instantaneously freeze. Pretty wild stuff. If you've ever seen it, it's really cool to watch. I've heard stories of Bering Glacier surge, and a professor, he was at Oneonta a while back. He was out there to watch the surge, and when it was surging, it was sending out a jet of water, about 3 football fields, and it's one of the biggest glaciers in the Northern Hemisphere. Sending out this stream of water, about 3 football fields, and then out of the front of the glacier comes blocks of ice, like the size of buses, just getting launched 100 yards down the way. Pretty wild stuff. It's one of those things you can die happy after you see something like that. It's easier to win the lottery and get struck by lightning than to see a glacier surge. Anyway, so there's a few zones here. So you get up higher in altitude. It's a lot drier, a lot colder. Snow coming down is more dehydrated. So within the accumulation zone, you have dry snow up high. Then you get down in this kind of wet snow. So a little more water content in the snow. In here, you're going to have melt. The melt process is going to take over. You're going to generate a little bit. You're going to generate a significant amount of water, and then this water, the percolation zone, is where the water begins to move its way down to the bed. So up here, you have a drier bed, I should say. It doesn't mean that there's no melt down there, but relative to the other part of the glacier, it's dry. So this is going to be dominated by slip deformation, maybe just sliding from till deformation. And then when you get down here, you move water to the bed, you lubricate the surface, and the glacier begins to speed up. Within this accumulation zone, the snow line does not define the end of the accumulation zone. A lot of water comes out, it stagnates for various reasons. Winter comes around and refreezes it. So this is where you're going to accumulate a lot of mass. If you get further down, then you start to remove a lot of mass down here. So this is the primary ablation zone. Glaciers flow. You continue to load it with snow. As you continue to load it, you start to bury snow, you start to add a lot of pressure. And then on the ablation side, you're removing mass, and so you have a negative pressure out here. So as you move up in altitude, you might get a little more snow. As you move down, you're going to have less accumulation. So your pressure gradient is going to change through here. What that means is that these dashed lines, you kind of think of these as basically your particle flow. So these particles are going to move all kind of, they're all going to move to, well, I shouldn't say together. These particles up here are going to move a little faster than the particles over here because there's the pressure gradient is much lower. So ice wants to move to low pressure. Same with water. So if you have melt, you can actually pump water up to the uphill. And then as you move the particles, since these are moving slower, these are moving faster, you start to get these inverted beds here. So this is a really good example. This is the Root Glacier out near McCarthy, Alaska. And these are, glacier flow is from left to right. This is about 10 kilometers from the terminus. So this is a nice area, the ablation zone that's been exposed. And you see these nice inverted layers here. All right, getting into ice flow. This is the good stuff. So this is the Root Glacier here. That picture was taken probably another, I don't know, a couple miles down glacier. This is the Kennecott Glacier. Few of the bigger glaciers. So this is the Wrangell Mountains right here. It's a volcanic shield volcano. One of the largest ice falls right there in North America. That's about 20 miles away. So you can get an idea of how much aspect that is. Just a few things, just some nice eye candy too, till we get into some of the more detailed stuff. Each one of these moraines, that's one tributary that's contributing to the main valley glacier there. So accumulation zone up here in the higher plateau area, and then it moves downhill into this kind of ablation region, and you have melt out. This is actually kind of a nice fact. So I don't know if anybody's familiar with this area. This was where huge copper production, or not copper mining area in the mid 1800s. This is the economics of the year kind of contributed to this region. There was around 1850, I can't remember the actual year, but I think it was post-Civil War. There's some mines right up here on the hillside. So they're mines, the tunnels that come into the hillside for copper and gold mining. And the glacier used to come up to this level back then. They had a railroad that came along the ice here, and they couldn't figure out why. The railroad kept collapsing and moving around. This is about the same time Louis Agassiz was working on a lot of the stuff on glacier flow and discovering that glaciers are actively flowing. Anyways, so the ice level, 150, 175 years ago was quite a bit higher. So we're looking at about 300 feet. This is a little more, this trim line right here is a little more recent. All right, kinematics. Kinematics are it kind of describes motion without considering the force that causes that motion. So we can kind of think about this: position, velocity, acceleration over time. Those are kind of how we think about it. Translational motion. So you're displacing a particle equally within this body, this rigid body, or whatever you want to call it. Rotational motion, slightly different. So you're going to rotate it. Center of mass stays the same, but particles within there are moving at different velocities. So you kind of see this sort of vorticity. Translation plus rotation is also a thing. So you have a rotated block and also displacement of the center of mass. Dynamics. So then we start to introduce force. Some sort of force. In this case, it might be mechanical force. So we have normal strain. If your force vectors are different, you might have dilation in one side, extension in the other. If they're all, you could have dilation on all sides. Pure shear. So you're going to see a gradient of your force vector along one side, and you deform your rigid body slightly differently. Volume stays the same, but the shape changes. In ice, what happens is in glacier, as ice deforms, it wants to kind of organize itself so that it is easier to deform. The basal plane is the basal plane. The top one is the weaker plane. So you're going to get, it's a lot easier to create slip. So the glaciers will actually align the c-axes so that you can have the basal plane perpendicular with the, not perpendicular, c-axis is perpendicular to the shear direction. And it's just the universe wants to find the path of least resistance, so it'll organize crystals in that way. This is a nice example of channel flow for those of you who look at it. So this is some ogives coming off that ice fall. And these are annual layers in here. So you have winter, summer, and they create these nice channel flow. So you have along the boundaries, you have zero velocity, and then as you move in, you have your maximum velocities. And this is just surface, so there's a lot of brittle deformation. If you come out here beyond the margins, you can actually see, it might be a little hard without zooming in, you can actually see block rotation. And so one side will extend in the block, and then it'll thrust ice onto that block as well on the other side. This is a nice little ridge right here. It's quite a bit, very pronounced. I'm guessing that is not a deformation mechanism. That's a melt due to melt because the mountain here provides shade to the surface of the glacier. So you remove a lot of energy flux at the surface. All right, yeah. All right, jump back and forth. These, I have some GIFs. So looking at the ice flow, I can make that bigger. What? Oh yes, I'm sure. I don't use PowerPoint. That one? All right. So it's a good example of the conveyor belts of glaciers. You have these, this is a time lapse put together by the USGS. This is nice because you can see a lot of you have these particles, rocks, and probably massive rocks that are just being carried on this conveyor belt coming out of the tributaries. So this is a nice clean textbook valley glacier. You see right here is a little bit of a surge glacier. And there's another one in here somewhere. I can't remember, but just gives you an idea of the little bit bigger picture on the flow. It's nice because these things do deform at a rate that we can see. If you study rocks, geodynamics, it's just kind of like, well, what you see is what happened 100 million years ago. Actually, I have another one. So here's a nice, this is a surge glacier or valley glacier that has a lot of surge happening in it. So these surge cycles, this is in the Himalayas. These surge cycles can be very dangerous because they send out a lot of ice at once. It could be a lot of water coming with that ice. And so in these valleys, there's a lot of towns, villages in these valleys, and you always hear of these massive floods and mud flows that come down and just wipe out entire villages. So it is a big hazard. Another reason why we why we're interested in ice. Right. I'll have more, don't worry. Oops. Did I not share that? I did. Okay. All right. We'll get to some wave propagation soon. All right. All right. So fabric develops. As I mentioned, crystals will orient given the stress field. And this is a study by Mons and others. This is Storglacian, which is one of the most studied glaciers in the world. What they did is they came in, they drilled a few cores in the shear zone, and they saw a very well pronounced crystal orientation. So when I say fabric, what that is, it's that's going beyond a single crystal, and we're looking at a swath, a distribution of crystals. So it's going to be, in some cases, quite a few crystals. These are all the C-axes. You're familiar with looking at stereo nets. That's what they are. And then we can kind of see this is just sort of the statistical representation of all that. So you see large pole figures popping up here. So, and that is consistent with the shear zone that they drilled in there. So, if you're interested in that stuff, it's a good paper to read. This is one I was able to be part of, the Jarvis Glacier. We did the same thing about the same time, actually, and we went out and we put in a few boreholes. So Jarvis Glacier, eastern Alaska Range. So it's kind of a dying glacier. This is the vortex of shitty weather, is what I like to call it. It's probably the worst place to camp out. I mean, it is really bad. I don't know how else to put it, but we were there for 16 days, and 9 days were a blizzard in our tent. And it's if you're some of these pictures, they're very inspirational because the alpine environments are very, very they're just there's so much grandeur in them. But if you ever go out there, if you're ever inspired to work on a glacier, there is going to be a lot of weather involved. So I've seen plenty of people break. Jarvis Glacier is an interesting place. It comes around the Denali Fault, actually runs just south of here. So we came in off this margin. There's a small little tributary that pops in here, and then this main trunk that comes off of the Silverback right here. This is a photogrammetry image we put together with some drones. We were camping about over here, the far end. So we had come out, and I've got a ton of stories on this glacier working here. I've been here more than any other person, but we'd come out, we had done a kinematic survey. So we went out and put GPS stakes out and came back and measured it. We went 1 year. We got there in September, put it out for the water year starts in October. So then we want to go September to September, get an idea of just the overall movement at the surface, and just kind of get an idea of the kinematics involved in to locate the shear zone. We came out, there's some other people working on there. They said, oh, at most you're going to get about 3 meters of melt. You get a meter of snow, and then 3 meters of ice will melt, which is a lot because it takes a lot to melt ice. So we were like, okay, well, let's be safe. We'll put our stakes in at 5 meters. They got 6 meters of melt that year, which is insane. That's a lot. I mean, that's 18 feet of surface lowering on the glacier. So a considerable amount. All our stakes were gone. I think we found a few laying on the surface, but they just got washed away in the massive flood that ensued all summer. So we came out. It's a little tricky. We had actually targeted borehole over here, and we came out. We did a couple weeks survey. The margin is actually quite a bit, really close. So we're looking at the margins right over here. So this glacier is decoupled from the margin. So this ice, everything within the margins just flows. It's all translational motion just flowing through there. Which, whatever. I mean, it's not uncommon for glaciers to do that. We went ahead, we drilled a couple boreholes. This is our deepest one. So this is a radar profile. We went in and tried to get an idea of the bed, the depth. And so we want one outside of the margin, one in the margin, and then one on the other side of the margin. So on kind of, I wouldn't say stagnant ice, but very slow moving ice. This is a nice radar profile, 100 megahertz, which doesn't get deep in a temperate glacier like this. By temperate, I mean that the most of the ice in the glacier is close to its melting point. So it's very, very viscous ice, very plastic, but it has a ton of water content. So this glacier is basically a giant aquifer. But you can see this cold ice gets a little deeper, shallower in the margin. And so the cold ice, radar propagates very nicely through there. Once you hit this warmer ice, you either attenuate it or you scatter it because there's so many water inclusions. But we get a nice visual on the bed, or what we think is the bed. I estimated at 80 meters. I think he put it at around 79, 78. One other thing to note, there's a lot of shear banding in here. So we kind of had an idea that there would be a lot of deformation within this zone. So what we did find, not a lot of fabric development, poorly developed fabrics, I should say. There's plenty of development, but the C-axes were kind of weak. So we're coming down in depth as we move from on the left side. So we're going top to bottom, left to right. So this is the shallowest core. So ice crystals are going to be much smaller. And as you move further in depth, you increase the crystals begin to grow. Ice crystals begin to grow. Eventually, you get to a point where they're very small. And so you have just a few C-axes to plot here. Makes it a little difficult to kind of build some statistics around it, but you can kind of see there's a little bit of development, but it's still fairly I guess, weak, I should say. So there's no real strong single pole of the C-axes. These are some of the thin sections that he pulled off of there. Really, the ice is really nice, like not nice shear banding in there, but the crystal orientations didn't really follow that. So it's kind of a big question in some of my research is why you have in some shear margins, you're going to have well-developed crystal orientation, and then others, as in this case, you're not going to have good orientations. JE was outside of the margin, nothing there. This one only went about 18 meters. 18 meters. The final depth of this was 78 meters. That's the lowermost core. So I was off by a couple meters with my estimate. I call that pretty good. All right. Another one. We're going to get into kind of the wave propagation stuff. So as I said, ice is kind of nice because it's thermally, mechanically, and optically isotropic. But if you think about when we're thinking about wave propagation on the GIF on the animation on the left, so particles, they're connected somehow, whether that some sort of electromotive force or shear or just grain sliding. They're connected. So when you move one, it's gonna impact the shear force or pressure on another. It's going to cause that one to interact with the next one. So that's kind of how the idea behind how we're going to propagate energy through this. If I were to add some sort of force on here, it's going to oscillate that one, this particle a lot more, and that's going to continue to propagate through the system. When I talk about anisotropy, so I think this is a good image, good animation of it. So if you have incident, polarized, or even non-polarized energy, light or seismic energy, what happens is when you hit this anisotropic medium, it doesn't quite happen this way because there's still inertia within the particle. So it takes time for the shear wave to split, but because it's looking for that path of least resistance, it's going to move energy onto that fast axis. This one's optically fast, extraordinary axis, or seismic energy along that fast axis. And so you will still maintain some energy along the other axis, but you're not going to lose it all. So don't want to, no spoilers. All right. And stop me if none of that makes sense. Back to this. Okay. So what I've done is a big part of my work at University of Maine. So I've developed this toolbox, the seismic radar. Oops. Seismic and radar toolbox. I couldn't tell you that, but SIDART is what we call it. The whole goal with this is to build open source cross-platform 2.5D modeling that has many applications, but we want to kind of get an idea to help. We want to be able to constrain or at least get some prior information on complex geometries. So if we go out and we do seismic or EM surveys, we want to know what our capability is, how we need to plan our arrays and our surveys, and then also it can kind of lead into building sort of analysis. So we collect our data, our analysis is already ready to go, or our analysis algorithms are already ready to go. Just kind of streamline it into there. It's great for education teaching because it really like to understand how waves propagate in I shouldn't say complex media, but complicated media. It's really hard to visualize. It helps me every time I look at this. You get a lot of understanding of the theory that was taught to you. Yeah, again, instrumentation methods. There's a lot of things in terms of instrumentation that's coming out. We have different types of radar systems, different types of seismometers. There are digital acoustic sensing systems, which are almost continuous. Basically, they almost sample at a continuous, I guess, line along the surface. So there's still a lot of things to kind of hash out with some of those in terms of the methods and just like their applications. So it's a good platform for that. It is another one of those kind of sandboxes, as I say, to help sort of visualize the behavior that is hard to see. It's a staggered grid finite difference time domain. If you know what that is, great, but it's a very simple discretization routine. We're working the quasi-static sense, so there's no real particle movement. So it's a good application for that. Finite element might be another one you've heard of. This is slightly different. I won't get into the boundaries, unless you're really into the modeling side of things. We could talk more about that. Bulk seismic attenuation. So that's still kind of, it's good to have attenuation in terms of the more the like finer scale attenuation that's happening for whatever reason, heat loss or energy loss due to heat. That's not incorporated in here, but someday, you know, I'll be when I get space on Oak Ridge supercomputers, maybe I'll add more finer attenuation. There's ways to calculate stiffness, so we've incorporated some sort of tools to kind of build good libraries and stuff like that, or generate your stiffness coefficients, connectivity, permittivity, those things. All right, I won't get too far into the math, but if you're familiar with this, we have the seismic. We're looking at the wave equation, stress and your relationship between stress and strain. So C is the stiffness tensor, and it describes the sort of how stress will be expressed, or how strain is going to be impacted by stress. It's just a couple definitions here. The EM side of things, there you have Faraday's law, or Ampere's law on top, Faraday's law, two of the primary equations in Maxwell's equations. Conductivity is going to kind of define in your EM is going to kind of define your attenuation here. And then we have our forcing functions. So this is our source, or whatever kind of force we want to add to the system to kind of perturb it to generate some energy. Yes, real quickly, staggered grid. So what that does is we're creating sort of these, every node in space is represented by, or represents either, in this case, maybe in the EM case, it could be the electric field on one grid, and then the half grid cells would be the magnetic field. And so you calculate one grid and then calculate the other grid based on that grid. And so the idea behind this, you can have higher order approximations of your derivatives without the computational intensity of a higher order Taylor series. We built in some snow and ice properties. I won't get into snow stuff so much in terms of seismic. It gets pretty wild. But yeah, so this is for a single crystal. This is kind of how it's calculated. Temperature, pressure are the primary components of that. For EM, the liquid water content is very influential on the wave speeds. So this is your permittivity, and then calculate conductivity from the complex. This is your complex permittivity. So I won't get into any of this. This is just kind of here for reference. I'll wrap it up. Okay. Yeah, so these are some of the basically validation stuff I've done. We have full control over the tensors, permittivity, conductivity, stiffness, and we could kind of generate these multipole fabrics. So this is a replica from the Mons paper. I built this up, and I can run that into a model and get an idea. If I were to go out and survey that, I can instead of having to drill boreholes, which cost a lot of money and are logistically tough, I can go out and potentially use a radar system or seismic system to estimate that. So the top, so this is basically, I have got three different types of materials here. The blue is the ice, so it's very low anisotropy, but there's a little bit. And then I have some other higher anisotropy. So There's some practical considerations in when you're dealing with these large anisotropy. There's some numerical dispersion here, which is evident. And so setting up the model is there's some little nuances that you have to consider. This is a replication of a survey done for the cross borehole. So these dashed lines are about where the boreholes are, and then basically I create this PNG, and this serves as my model domain. And I have, for each layer, I have different temperatures. This was a nice paper because they went in and they had those boreholes, and so they were able to measure the temperature and get good estimates on it. So this replicated their study really nicely. Yeah, common offset. I won't get into it. This was something I put together with a colleague. She was interested in how scattering affects the radar signal. But what I did do, I will show you I'll just go through the next couple of GIFs. So, and we'll wrap it up. But so this is that model there. This is nice because right down here, we hit a critical angle of incidence, so there's no reflected wave. Instead, this refracts. You see scattering off of the water. She was interested. She thought she had seen water very deep in the glacier, which is not something that is common or at least observed until you get to the bed. So internal in-glacial water above the bed is not expected, but she was seeing some sort of scatters in her profile. This was an early model, so it's not super well polished. We get into seismic stuff. This was something. This was I'm trying to excite surface waves here, so you can kind of start to see these surface waves start to develop. Higher frequencies move a little slower than the lower frequencies, so you create dispersion. All right, and then finally, this is a body wave model. So I'm trying to excite body waves. This is a really nice one because you can see shear wave refractions, and you can see P wave refractions. You'll kind of see this. There's this refracted wave here. There's a head wave. This is a shear head wave coming up, and then your main body wave. But yeah, I think we're out of time. Yeah, but we're getting there. So that's kind of some of the work I've been doing. That falls into the validation aspect of things. So this is just an image from a common offset that I had created. All right, and then finally, the GIFs. Yeah, so there's some analysis. I won't get into it too much, but some analysis on the surface waves, body waves. So everything checks out. Everything's working well. And then I'll just leave you with this. If you have any questions or just thanks for having me. This is out near the Kennecott Glacier. But this is really interesting kind of specimen. So it's a rock that has exhibits kind of turbulent flow. I don't know. Turbulent flow in the solid states kind of blows my mind. But anyways. All right. Any questions? Oh, yeah, thanks.